So in any linear algebra class, in any advanced or more or less advanced linear algebra class, the first thing you'll probably talk about is going to be a vector space or vector spaces in general. So what I'm going to try to do in this video is help you understand the definition of a vector space and what is really meant by a vector space. Now, usually how the definition of a vector space starts is suppose V, could be any letter, but usually we use V. Suppose V is a set of elements that we also refer to these elements as vectors. Okay? Well, already there's like a part of this definition that needs a bit of clarification. Because if you don't know yet, well, a set is just a collection of elements. Set is a collection of distinct, right? So none of the elements are the same as the others, or no element is equal to another element. A set is a collection of distinct elements, right? So if you want, just think of a set as this sort of huge space. It doesn't matter what it looks like, and we have dots that sort of represent elements, or in this case, in the case of vector spaces, vectors, right? So we have A, we have B, we have C, and we have D, and whatever. It doesn't need to be finite. It could be infinite. It really doesn't matter as long as it respects the definition, which we're going through right now. So in this case, we would say, A is a vector that belongs to V. Okay, so that's the first part of the definition. V is a set of elements that contains, right? So this is the second part of the definition, that contains a field. Okay, a field. Okay. So that's the second part I want to talk about. What is a field? Okay. Well, a field is actually really just numbers, and if you're a mathematician watching this video, which I doubt, because why would you watch my videos, then you'll probably say, well, you really should call it a number. But for the purposes of this sort of class, you sort of just refer to fields as sets of numbers. So it's a set of numbers, and those numbers have a certain characteristic. So for instance, if you were to take the natural numbers, right? Natural numbers have the characteristic of being whole numbers that are positive or zero, right? So we have 0, and then we have 1, 2, and so on. Okay? Or we could take the set of integers, right? Or the field of integers, really, which is just all of the integers, negative and positive. So it goes from minus infinity, let's say minus 2, minus 1, 0, 1, 2, and then plus infinity, right? So all of those are whole numbers. The one that we see the most is the real numbers. So the real numbers is a field of numbers that encapsulates almost all of the possible numbers in the world. The only one that it doesn't encapsulate is the complex numbers, which I'll probably reserve for another video. So the set of real numbers is, it can be anything really. It could be negative 2, it could be negative root 2, it could be 0, it could be 1, it could be pi. Pi is irrational, but it's real. It could be, 77. It really doesn't matter. It's really arbitrary what number you choose in the real numbers. The characteristic is just that they sort of encapsulate all of the other fields. So I missed Q. Q is a set of rational numbers. So rational numbers are any numbers that you can express as A over B, such that A and B belong to Z. So the particularity of the real numbers is that it can be either rational or irrational. Okay, the only thing it can't be is complex, which I'll probably talk about another time. Okay, so that's sort of the sort of building block of my definition. We have that V is a set of elements that we call vectors, and we have that V contains a field, or we also refer to this as scalars, right? We know them as scalars, right? So that's the sort of ingredients of my definition. Now, like a recipe, when you have ingredients, you need instructions. So the instructions to this definition, or the sort of operations in this case, are, so I'll continue the definition over here. With the two following operations. Okay, so two operations are defined on any vector space, and the first one is known as vector addition. So vector addition is known as the result of taking two elements in V. So you take two elements in V and you add them up, right? So this is the vector sum, and it also belongs to V. So this is what is known as vector addition. When you take two elements in your vector space, you add them up, so the operation is the addition, and they belong in V. Okay. The second operation is known as scalar multiplication, and it just does what you think it does. You have a scalar, let's call it C, that belongs to a field. By the way, I didn't write it here, but you usually represent a field by F. Okay, F. Okay, so you have a field, you have C that belongs to a field, and then you have U that belongs to your vector space. Then scalar multiplication is that thing that gives you C times U. So C scalar multiplied U, and this result belongs to V. So it's the operation that sort of resembles a scalar multiplying your vector. Okay, so these are the two basic operations that you have when dealing with vector spaces. So the definition really is V is a set. Okay, it contains a field F, or scalars. Okay, and it has two basic operations. So it has two basic operations. Now, of course, we're not done yet. The most important part is that V must satisfy. V satisfies the following axioms. Okay, and depending on which reference you use, there's from 5 to 8 axioms so axioms are kind of like conditions that need to be met, that must be met, conditions that must be met, so that V is a vector space. Okay, so what are these conditions? Well, I'm running out of space, so I'm going to write them over here. Okay, so over here. So conditions or axioms for my vector space. Okay, so the first condition is commutativity. So I'll call it axiom 1, also known as commutativity. And this just says that for all U and V that belong to my vector space V, U plus V must equal V plus U. In other words, addition is associative. So It does commutative. Sorry. So it doesn't matter if you add u to v or v to u. The result will be the same. The second axiom is associativity. Associativity. Okay, and this axiom says that for all u, v, and w, so this time we have three vectors that belong to my vector space V, u plus v plus w is equal to u plus v plus w. In other words, what this is saying is that if I do this operation first, and then I do this operation second, then it comes out to the same thing as adding v plus u first, and then adding u to that result second. So they do the same thing. So the third axiom, the third condition, is the existence of, whoops, I want to be in white. The third condition is the existence of a zero vector. Existence of a zero vector. Zero vector. Okay, and what on earth is a zero vector, right? A zero vector that we usually represent with a 0 and an arrow. Okay, well, the zero vector, it's by definition, what it means is that if you add something to the zero vector, then it'll give you that. It won't change it, right? So the third condition is that there exists, right? So this is just there exists the zero vector that belongs to V, such that if you take such that for all u belonging to V, if you take the u and you add the zero vector 0, then it'll just give you u. In other words, what this means is if you take your zero vector, so this is your zero vector, and you're doing the addition operation, then it will not affect your u vector, right? It's just gonna be there and then sort of disappear. It's gonna disappear, I guess. Disappear in the sense that the plus 0 vector is gonna do something, but in fact it's gonna let the u be unchanged. So the u is unchanged. Maybe I'm going too much into depth with this, but it's just to make it absolutely clear. Okay, so axiom 4 is that, so axiom 4 is, yes, it's the additive inverse property. Additive inverse, okay? So the additive inverse says that for all u belonging to V, there exists a vector that we denote that we denote the additive inverse, which we can sort of just write as minus u. And this axiom says that when we add u, so such that u plus minus u, so that's my additive inverse, equals the zero vector. Okay, so this is saying that if you take u and minus u, in other words, the opposite of u, then you'll get the zero vector. So that's the additive inverse property. Okay, then axiom 5 says that for all u belonging to V, 1, so the scalar 1 that does the operation, that does the scalar multiplication operation on u, also leaves u unchanged. So u remains u. So 1 scalar multiplied u is just u. Okay, so that's what that means. There's no real name for that. I mean, maybe it's called the unitary. I'm not exactly sure. Then axiom 6, okay, is says that for all u belonging to V, and for all the scalars a, b, that belong to the real numbers. So in this case, our field is the real numbers. So this is, so this is my field. Okay, field F. So in this particular axiom, my field F is R. You could probably make this more general into C, but for the purposes of this course or this sort of material, we just keep it for the real numbers. So it says that for all vector u in V, and for all scalars a, b, and r, if we do a scalar multiply b scalar multiply u, then it comes back to the same thing as doing a times b. So this is just a multiplication in numbers. So this is I guess you can call it a number multiplication. Okay, so it's the same thing as doing a times b scalar multiplied. So I'll do a dot for the scalar multiplication. Dot u. Okay. So that's pretty straightforward. It's not saying anything that would surprise you in any way. Then my seventh axiom. So axiom 7 says that for all u and v that belong to my vector space V, and for all a that belong to my real number, real numbers, if I do a times u plus v, in other words, if I do a scalar multiplied the vector addition of u and v, then it comes back to the same thing as doing a scalar multiply u plus a scalar multiply v. Now, when I say it comes back to the same thing, it's these are conditions that you have to check. So you have to check if this is true to see if it's a vector space. And the definition of a vector space is a set such that the elements in that set they check. So all of these conditions are checked. And then my last axiom, which is axiom 8, says that for all u belonging to V, and for all a and b, so for all scalars a and b belonging to the real numbers, a plus b, so in other words, this is the number addition. Okay, so doing the number addition scalar multiplied, so I'll do a dot for my scalar multiply u, is the same thing as doing a scalar multiply u plus b scalar multiply u. Okay, and so I just want to emphasize that this dot here, so when I do a dot, that's just doing the scalar multiplication. Probably should have done a different color, but you get it. Okay. Okay, so that's the definition. After all of that, so we've basically come to the conclusion that the vector space definition. So I can sort of do a summary here. So summary. Okay. So the definition of the vector space. So the vector space definition, vector space, is defined as a set, right, that contains vectors or elements. So that contains vectors and scalars, right, with two basic operations defined. So it has vector addition, and scalar multiplication defined, and it follows 8 conditions, which are the 8 axioms that I just talked about. So that's what a vector space is defined as in linear algebra.